Welcome everybody to the NeurIPS 2022 workshop on challenges in deploying and monitoring machine learning systems. Today, I am honored to be delivering one of the workshop keynotes on security in production machine learning systems. Just as a heads up, you will be able to find the slides in this link above, where you will be able to access all of the resources covered in this session. A little bit about myself. My name is Alejandro Saucedo. I am Engineering Director at Seldon Technologies. We are a company that focuses on providing products to enable deployment and monitoring of machine learning systems. I'm also Chief Scientist at the Institute for Ethical AI. This is a research center based in the UK that focuses on contributing and developing frameworks that ensure the responsible design, development, and operation of machine learning systems. And I'm also a governing council member at large at the ACM. So today we're going to be diving into a very important topic. So this is the topic of security in machine learning. And something that is very interesting is that there's a lot of resources about that explore basically how to apply machine learning into security challenges. So basically things like spam detection, malware detection, etc., etc. However, when it comes to best practices and resources to applying security into machine learning is still an emerging field. And one of the things that we want to do today is to highlight some of the best practices and resources that have been identified and that are currently in the midst of being explored. And the way that we want to approach this is in a very similar way to which it's approached in the general software space. And in the general software space, we know that there is a broad range of different tested and proven methods, techniques, tooling to enable software practitioners and security practitioners to enforce these best practices. And the way that it is being approached is in basically acknowledging that it's impossible to make systems completely unhackable, right? Or completely fully secure. However, what it's possible is to mitigate a reasonable amount of undesired outcomes through best practices, through tooling, through automation, etc., etc. However, the thing that we will also want to remember throughout the session is that even though these solutions will be technical in nature, they will ultimately still rely on humans and process, right? And that tends to be one key highlight to remember consistently when it comes to security, irrespective of whether it is applied in machine learning. And we're going to be using the topic today of MLSecOps, which is an emerging word that is aiming to encompass basically the operationalization of security in machine learning systems, as opposed to just machine learning models. And this is basically the extension of DevOps, security, and general software with security into the machine learning operations as first-class citizen. And this is the intersection of the machine learning infrastructure itself, but also with the developer operations, data science operations, and the security operations themselves. So that's basically the topic that we're going to be, I guess, exploring under the umbrella today. And we also want to take a step back and understand why is production machine learning so challenging and what are the challenges that it introduces in terms of security that go well beyond the traditional software space. And why can't we just take traditional software approaches and just bring them into machine learning one-to-one? Why do we have to really give some thought about that and still get inspired from software best practices, but really kind of ensure that they're encompassing machine learning? And some of this, of course, this is not exhaustive, this list, but some of the challenges that we face as practitioners is that when we're using machine learning, we actually require what we can refer to as specialized hardware. So this could be GPUs, TPUs, but also large amount of memory, large number of CPUs for concurrent vertical scaling, etc., etc. There are also complex data flows, right? Now we're moving away from the model-centric view of our machine learning systems, and we're moving towards that data-centric view of not just productionizing models, but productionizing machine learning systems. And these ML systems come with complex data flows that involve multiple steps that can affect things upstream and downstream. And these dependencies and data flows can be significantly complex. There are also challenges in the reproducibility of components, right? If something goes wrong, it's not just about getting the code and rerunning it. That machine learning atomic unit consists of the code itself, but also the artifacts, the relevant inputs, the outputs, the data it was trained on, the configuration, the environment, and potentially in some cases with pipelines, the different sort of like stages of those pipelines. So it is important to make sure that the level of reproducibility, auditability is in place in order to achieve the requirements of the use case. And finally, because machine learning, data science is so close to the use case, it also has heavy compliance requirements. So there's a lot of considerations to take into account. Now, from a more, conceptual perspective, let's actually see what are the limits of our thinking when it comes to just traditional software, right? And this could be seen kind of like as the artifact store from a practitioner view, but this will give us an understanding of why it's so different to the traditional sort of like software code perspective. So let's imagine that we have a set of data sets, right? Data set, A1, data instance A1, A2, all the way until AN. We then may have some machine learning models that are trained on this data, right? So model artifact A1 gets trained on this subset of data, then A2 on another subset, AM on another subset. So we have a bunch of artifacts, but we can also have different models trained in different data sets, right? We may have like other models B or C, et cetera, et cetera. Now we actually want to operationalize these models, right? So not only we have the artifacts, but we now want to actually get value from these artifacts. So we may actually deploy artifact AM in environment X. And then we may deploy this same artifact in another environment, right? So we have now basically the same artifact, but deployed in different contexts, different environments. And then similarly, we may actually have a pipeline that may make use of this particular model, right? A preprocessor, a tokenizer, a vectorizer, a text cleaner, and then a potential, second post-processor or model as part of that machine learning system. So now we see that we have a different sort of relationship that we have to consider when it comes to our machine learning artifacts, right? The different sort of considerations of the data that is involved, the artifacts, and the operationalization of those artifacts, as well as the potential risks that are introduced at each stage of your machine learning lifecycle, right? So the many-to-many relationship that you have in machine learning systems. And of course, instead of just tackling this from scratch, we can take a step back and look at what's available in the general software space, right? And the general software space has had to really tackle challenges on security at web scale, right? This is at massive, massive scale. So some of the challenges that we're now seeing in the production machine learning space, there's a lot that we can learn from the general software space. One of these resources that we're going to be looking at today is a resource that goes under the name of the OWASP Top 10. So this is the Open Web Application Security Project, which basically releases every year and tries to highlight what are the most common security vulnerabilities in the web ecosystem, right? So this could be things that in the web ecosystem are much more common, things like SQL injections or broken access control or insecure kind of like design. So these are things that would be more relevant to that space. So how can we actually explore bringing them into the data science space? Well, so fortunately, there has been quite a lot of thinking and a lot of great initiatives that have been exploring this. The Linux Foundation has published a set of high-level principles that several of the open source projects have been, adopting or leveraging as North Stars. These principles themselves cover things around explainability, reproducibility, robustness. But of course, the thing that we are interested of today is security. And one thing that has been quite interesting when it comes to exploring security in the context of these high-level principles is that to large extent, security encompasses pretty much all of the other principles, right? Security encompasses privacy, encompasses accountability, right? The need for accountability, but it also requires considerations for things like explainability, right? Who should have what explainability accessible in what contexts, right? So there are security considerations in every single other step of the other principles. And similarly, now as part of the Linux Foundation, one of the work streams that has been created has been exploring basically what are the security considerations in the end-to-end life cycle of a machine learning model. This is basically the proposed ML workflow from the Linux Foundation that encompasses basically the abstracted view of the traditional machine learning lifecycle, basically the data operations for feature engineering, data splitting, the model training and experimentation, and then the model deployment, monitoring, fine-tuning, and then retraining with the full lifecycle. So we were to take a step back and ask the same question of what are the steps around this lifecycle that can be affected by potential security vulnerabilities. And these are the areas highlighted in red. Basically, every single point of the machine learning lifecycle has potential security vulnerabilities. And this is why then we were able to take a step back and ask the question, well, what could be some of the most common or some vulnerabilities that would be worth having a look at and highlighting and exploring? And this effort has now come under the name of the MLSecOps Top 10. You can actually find this resource in this link. And this aims to actually identify 10 common vulnerabilities that as machine learning practitioners, we may actually come across at some point in our life cycle, in our development. And what we are going to be doing today in this session is we're going to be wanting to delve into this 10 machine learning vulnerabilities and try to understand how could they be exploited, and how we can actually approach best practices to avoid them and mitigate them, right? Mitigate them is the right word. So that's what we're going to be doing today. So really, we're going to be taking a practical crash course where we're going to be deploying a machine learning model, or we're going to be taking some machine learning data, training data. We're going to be training a model, we're going to be deploying that model, and then we're going to be exploring at each stages how this process could be exploited and what are the things that we can do to avoid going into those vulnerabilities. So, of course, this is not a session specifically delving into the nuances of machine learning productionization, right? We're going to have a TLDR or a TLDW for this. But if you're interested, you can check out some of the other resources, linked in this session, as well as, of course, the rest of the sessions in this workshop that are going to be talking a little bit more in detail about the machine learning deployment, the monitoring, et cetera, et cetera. So for that sort of TLDW or TLDR, what we're going to be doing hands-on is going to be converting a machine learning artifact, in this case, a scikit-learn artifact, into a fully fledged microservice. And we're going to be using this tool called Seldon Core to deploy it into a production, into a Kubernetes cluster, right? So we're going to be taking this machine learning model, and then we're going to be converting it into a fully fledged microservice with a REST API that is running in a Kubernetes cluster, and we're going to be actually interacting with that. So let's have a look at basically doing that. So we're going to be using these resources, this Jupyter Notebook, which you can find in this repo. You can run it yourself locally together with the setup. So the first step is actually getting that artifact, right? So let's get this scikit-learn dependencies installed. Basically, I already have them installed. So, we don't have to wait until that, fully runs until the end. Now we can import scikit-learn, and we're going to start with the hello world of machine learning, which is the iris dataset. We're going to be taking this dataset, and we're not going to be following best practices. We're not going to split the data, but we're going to be training a logistic regression model with our training data. So once we've actually fit that data, we can see that we can now predict a specific unseen data point, even though this is a seen data point. And now that we have an artifact, how do we actually convert it into a fully fledged microservice, right? We have to somehow, save this artifact and make it accessible so that it's available in that microservice. The recommended way to export artifacts in scikit-learn is using basically Pickles, right? In this case, dumping our binary into a file, which in this case is called model.joblib. And if we have a look at what's inside of that model.joblib file, this pickle file, we can see that it's basically, partly some gibberish, but you can see here that the format is basically the module, the Python module that it should use, the Python class, and then the parameters to initialize that class, right? So this is basically what we can see on the binary data that is in our current pickle. And we can now deploy our machine learning model, right? As I said, Kubernetes works with config files. So we can say, hey, our artifact is here. We want to use a scikit-learn model. We want to deploy that model. And once it's deployed, we can see that it's basically running. And we can run a request against that running model, right? So the input is an array. The output is the prediction, which in this case is the class of index 2, right? So we have now a deployed machine learning model. Now let's actually have a look at what are the security risks that we're going to try to exploit today. So the first one is going to be on loading model artifacts, then accessing the unrestricted access to the model, the vulnerabilities on the dependencies, on the code, on the runtime, and then some honorable mentions as we won't have time to cover fully in detail. So the first one, we're going to be delving into the artifact itself, right? And so pickles themselves are something that, for some reason, data practitioners just love using it. I mean, we know the reason, right? That's often the recommended way to export artifacts from Python. But we can basically just joke around that and say that everybody in the data science community loves pickles. So we often hear and we are aware that pickles have security vulnerabilities, right? But often you think about what would be those security vulnerabilities and how could they be exploited. Today we're going to be looking at one of the large number of examples in which pickles can be exploited, and this list is actually pretty large. So let's actually load that pickle that we just saved, right? We can see that we can still predict data from that pickle as expected. And now we're going to be meddling with some of the internal functions of how Python exports pickles, right? And that is the reduce function. This is the function that actually explains or provides Python the details of what module, what class, and what parameters it should use. And if we actually override that reduce function with our own function, which in this case is going to be running from the os.system module, this parameter, which is basically just like a string, encoded string to hide from people that are curious, that want to see our exploit, that is going to copy all of the environment variables, all of your environment variables into a pon.txt file. But this is a Linux command, so you can do anything, right? You can run a Linux, you can send an email, you can do whatever you want, right? So in this case, we're just going to be actually creating a file, and we can check that the file was created, right? So let's override our model.save class with that particular function. Let's then save that pickle, right, into this unsafe folder. And if we now have a look at the pickle to see what's inside, we can see that it's a little bit different, right? We can see that now, instead of actually loading it from scikit-learn, it's loading it for the model from the module POSIX, the class system, and then basically it's running here. We can even see the base64 decoded value that is copying your environment into the pon.txt. We can then actually just deploy that model, right? We're deploying the unsafe model. And when we actually see in our Kubernetes cluster, we can see that the unsafe model is running, right? It's running as if nothing was going wrong. But if we can actually see inside of the actual container, we can see that the pon.txt file has been created. And the first 5 lines, we can see that all of the environment variables have been copied. If we actually load that pickle locally, we can see that the pon.txt file is also being created, right? So, well, thankfully I don't have any secrets, so you can see any secrets in my folder. But this is one of the many ways in which pickles can be exploited, and it is one of the reasons why we have to ask, well, if we know that pickles are such a common potential vulnerability risk, why are so many open source libraries and ubiquitously adopted libraries using and recommending pickle as the form to export, right? And this is things like from the scikit-learn documentation, some other frameworks like Keras or PyTorch that use or used to use pickle for exporting. And ultimately, there are multiple ways in which we can explore this, right? One of them could be perhaps whether we need to actually scan all of our pickles and try to verify that there's no malicious code in the pickles. However, if we look at the traditional, software approach, is that when you're dealing with artifacts and resources that can execute code, right, similar to containers, similar to perhaps like artifacts that are published for C++ binaries or Java binaries, the approach that tends to be in those contexts is that of trust or discard, right? You need to make sure that for the pipelines that are creating these artifacts, there is a level of security that enforces and ensures that trust or discard mechanism. And now we're actually seeing some really interesting approaches to introducing like artifact signing to ensure that the artifact was produced by a trusted resource. And of course, there are some interesting projects that are exploring the question of Python Pickles scanning, although they are still very emerging and very nascent. There are other projects that have been recommended much more significantly on how to export your machine learning models into standardized formats, like, for example, the ONNX format, right? This Linux Foundation project that allows you to not only export into a standardized format, but also optimize your models so that they can be run into heterogeneous hardware. So there are certainly a lot of tools that can be available, and we're going to have a look at some of those. Now, so this is on the Pickles. Let's move to the next step. This is around unrestricted access to the model. The first one that we're going to be exploring is unrestricted access to the machine learning model endpoints themselves, right? So if you were to deploy a machine learning model, as we just did, if we allow you to actually access the machine learning artifact, the machine learning endpoint itself, that means that you would be able to consume that endpoint without restrictions, right? And one of the interesting areas of machine learning that have been able to exploit unrestricted access to model inference is adversarial attacks. And this is basically the ability to create what is referred to as an adversarial example. This is a input to a machine learning model that can actually fool the model whilst still fooling the human that perhaps would actually see that model. In this case, there are some visual examples, and adversarial examples of images tend to be the most intuitive. This is basically images that have adversarial noise added that is indistinguishable for the human eye, but that actually changes the prediction of a machine learning model, right? So in this case, it's basically the picture of a horse, but then with adversarial noise, it's predicted as a dog. Similarly, from a truck into an automobile, from a dog to a horse, right? So in terms of some of the adversarial examples, there are some really interesting resources that we provide in terms of practical ways of developing and creating some of these examples, which is provided by one of these open source libraries called Alibi Detect. So Alibi Detect provides a broad range of different algorithms for adversarial detection, but also outlier detection, drift detection, etc., etc. So here you can actually leverage some of the examples to create basically an adversarial attack, generate some adversarial examples, and then being able to exploit a particular machine learning model. And what is more interesting than just basically the adversarial attacks themselves is some methods to mitigate the potential risks of these attacks and these adversarial examples with the concept of things like adversarial detectors. So these are potentially asynchronous or synchronous components that you can put as part of your machine learning system that would be able to monitor the inputs of your model and highlight whether a particular instance is an adversarial instance, right? This would, of course, be a potential solution, but it is not the only solution, right? You are not required to come up with, potentially complex adversarial detectors for every single one of the models that you deploy, because it is also possible to approach it by, restricting the access to your model endpoints, right? By introducing role-based access control, authentication, authorization that we're going to cover later on, you have multiple different options that allow you to specify which users have access to which models. And this also applies not only to machine learning models, but as we mentioned briefly, it also applies for advanced operational requirements of machine learning, such as explainability, right? The explainability techniques and interpretability techniques have to be accessible, of course, to the relevant domain experts, but also have to be restricted so that they're not accessible just to absolutely everybody. So that's also something to consider. The second part of access to the model is not just access to the model endpoints, but also access to the model artifact. Once, if malicious players are able to access the artifacts themselves, there is often an assumption, perhaps a naive assumption, that a model that has been trained from a data set would obfuscate completely that data, right? However, what has been identified is that in some really interesting research, it is possible to extract some of that training data in some contexts, in this context being large language models, right? So, ultimately, this could potentially be susceptible to an attack from a malicious player in not just the case of deep learning models, but also in some machine learning models that actually do keep meaningful and reversible information from the training data itself. So now let's move to the next one, code, right? And as data science practitioners, machine learning practitioners, often, when working in a Jupyter notebook, you may think to yourself, well, I'm going to just write this machine learning training logic, and this may not be susceptible to perhaps the traditional cybersecurity or security vulnerabilities that would be from the general software space. However, one of the things that has been highlighted is that machine learning is also code, right? And code is susceptible to common vulnerability exploits. So libraries like TensorFlow, Keras, and many others have been actually susceptible continuously to a lot of vulnerability exploits that then get remediated. And also, this can be mitigated by using best practices when interacting with these different interfaces. A common one that maybe some of the practitioners in the audience may actually have come across is a relatively recent exploit with the YAML library. Well, it's no longer recent, it's a couple of years back, where actually the model from Unsafe had kind of an exploit that would have been in place in many machine learning code bases, because they would actually be using the YAML loading or the JSON loading from this library. So this is why it's important to make sure that whilst it's not necessary for every single data scientist to be kind of running manual scans, is that code that is produced for machine learning contexts can also benefit from the tooling that is available, such as software scan, automatic static scan tools, etc. An example of this, which we are keen to showcase, is that there are a broad range of open source tools. In this case, a tool called Bandit that allows you to actually be able to run this against your current code and highlight whether there are potential security vulnerable paths. And there are a lot of different tooling, even from the closed source side, that you can leverage for this. A reminder, of course, that Jupyter Notebooks are also a consideration, right? Just because it's in a notebook, it doesn't mean that it's security risk-free, right? Just a reminder. Now, for the next area, dependencies, right? So if you pull a library like scikit-learn, you may actually think to yourself that by pinning all of your dependencies, you may actually be freezing all of the potential supply chain of software that is involved within your environment. However, the challenge, and this is specifically to Python, is that if your third level, fourth level dependency doesn't pin its own sub-dependencies, then you're going to have a situation where if a sub-dependency pushes an update, you're going to end up running into that new update. And of course, many of us have run into this issue just from a more kind of naive perspective of going home on a Friday with the code working, coming back on Monday and realizing that stuff is broken, and realizing that it's broken because nth level dependency got updated. However, recently we have started to see a significantly larger number of situations where security vulnerabilities have been introduced through that software supply chain, right? And this has actually been quite highlighted due to the impact it has had, right? So this is not just through, PyPy type packages, but also through other languages that have been susceptible to what is now referred to as the software supply chain. So software supply chain security is absolutely key. And for example, us, we have been developing this project called ML Server, which is an open source machine learning server, and we have been collaborating with other projects like ML Flow to identify how to mitigate this challenge of dynamic dependency supply chain vulnerability. Right? In the past, you have situations where your machine learning container may actually install everything every single time that it runs. What we are now exploring is treating this in a multi-stage flow where you can actually install the dependencies once, whether it is in your Docker image or in a Conda pack or an exported file that then is signed even potentially, and then actually that is run in production as opposed to dynamically installed. And of course, there are a lot of tooling that you can leverage to address your supply chain vulnerabilities. In this case, we're going to be looking at things like pipdep tree, which allows you to visualize what are your dependencies. Here you can see that even though we only have this 4 dependencies installed, you can see all of this dependency tree that is generated, many actually that are unpinned. So if we want to actually deal with this, one naive approach would be actually doing pip freeze into your file and actually reinstalling from that. But there are now better approaches, such as things like Poetry, which is a dependency manager that allows you to create a lock of your environment and actually be able to manage that kind of parity of environments with a log file. You can also leverage tools like Safety, which allow you to check the dependencies from your environment, running safety check to see if you have any potential vulnerabilities. So here, for example, it tells you things like Django. I don't know why that is in the environment, but there are vulnerabilities there, and then you can address them. And you can also download things like piprot, which basically tells you which of your dependencies are outdated, right? Is which of the dependencies you have to actually have a look and try to update, because outdated dependencies could also be like potential challenges to address kind of like in your different contexts, right? So it's important to make sure you manage this. And for example, in the context of GitHub, you would actually have something like the automatic dependency check that would verify those different components. So it's important to validate those areas. So ultimately, it doesn't end on tools, right? It also is required on your environments, right? So if you run like Poetry on a specific version of Poetry, and then you rerun it on a newer version because your package manager changes, that actually is another dependency that you have to manage, right? So it doesn't just end up there. The final one that we want to talk about is images. And this is kind of like the final one, just because there's a lot of content. This is basically once you actually generate those runtime. If you remember, when we deployed our artifact, we actually deployed it on a container. We can actually run scans, in the context of, the deployment of our, open source framework, Seldon Core. We actually run the scans on every release. And you can actually run using open source tools like Trivy to check if images actually have any vulnerabilities. So that's actually how, we run some of our current scans. And a set of honorable mentions. We're not going to be diving into details, but of course, given that this is a data science focused session, we wanted to just highlight more of the data science, particularly specific areas. But there is a long list of considerations when it comes to your infrastructure, right? Your data ops infrastructure, your ML ops infrastructure, your things that we only skim through, like role-based access control, authorization, encryption in transit, encryption at rest, hardening of the different stages of your pipelines. And the reason why this is important is because this becomes, again, to what we were saying, a human problem, a process problem, as opposed to just a tooling problem. And if you think about it, this is because you have different personas involved in the development of your machine learning resources, right? You may have some data scientists that are creating and training machine learning models using a broad range of heterogeneous tooling. You may have machine learning engineers that are building sort of like use case pipelines to productionize these machine learning models, right? And creating those runtime engines, these images, et cetera, et cetera. And then you may have some of those DevOps engineers that are handling all of the MLOps infrastructure, data ops engineers that are managing the data ops infrastructure, the Kubernetes clusters, the cloud provider services, and this requires several levels of practitioner best practice involved. And of course, we have to remember that this also evolves as your data science requirements grow, right? So perhaps if you have only a small set of machine learning models, you have your data scientists owning the end-to-end life cycle. They're responsible for the security of that end-to-end, and maybe security in itself is not kind of as ingrained as it would be in a larger operation, right? If you have a larger number of models, that's when you would start including machine learning engineers to be able to, or software engineers to build automation, manage the tools, manage the infrastructure. And once you have kind of a large operation of your machine learning, that's when you start having MLOps or DevOps engineers operating that large scale infrastructure. And you can see that as you go into that stage, you have a significant larger requirement for automation, standardization, control, security, observability, reliability, many of the things which gratefully are covered in this workshop today. So yeah, with that, we have been able to actually cover a very broad set of, I guess, deep concepts through the ML SecOps Top 10, which I, want to put a call to action, as this is a work in progress. If you want to actually contribute or get involved, we would be super keen, as the area of machine learning security is still an emerging field to be explored. And of course, we didn't want to just end this session with presenting problems, right? We also wanted to present some solutions. And we've actually been putting together some resources to address some of this, what we can call flawed machine learning, into secure ML. And this is basically a template that allows you to be able to get started with a machine learning project for you to be able to, in a way, kind of like allow your data scientists to start with best practices out of the box, right? So this is basically using Cookie Cutter, which has a bunch of options. It's on basically this repo. And if we provide basically the baseline parameters, which is just the variable what the project name is, it generates for us a base template project. And if we have a look at the project template itself, we can see that we have a bunch of things like a Docker image. We have a base Python wrapper that we can use and put basically our artifact loading there. We have a set of project, like a poetry project dependencies, so that we have consistency of the environment. And then we have basically the commands to be able to run security scans, etc., etc. Here you can actually see some of the scans that we can do from the project itself. So I would actually, do a call to action for people to try it out and contribute to this tooling to ensure best practices in security for the machine learning ecosystem. And of course, we would like to highlight a lot of other resources that you can check out. So, we have talks on CI/CD, production monitoring, machine learning acceleration, that as well as another keynote that we did, that I did last year on AI ethics and responsible AI that you can delve into. So I definitely recommend for you to check out. The resources, again, they're available in this repo, and you can access the slides on this link. And with that, thank you very much for your time. I hope you enjoyed this keynote on security in production machine learning systems. And I hope you enjoy the rest of the NeurIPS 2022 workshop today. So I look forward to your questions. And with that, thank you very much.